Fluid dynamics. In the last chapter, we studied the static fluid. We took a quantity of fluid in a container and we calculated the difference of pressure between 2 points, any 2 points. And we took into account just the height and the distance between these 2 points. And we don't take into account the velocity because we don't have flow of fluid. Just we have a static situation, static configuration of fluid. And we calculated for a static fluid, if we have point 1 and point 2, we calculate the height in function of the lowest point. Here we have h1 and here we have h2, and p below equals to p above plus rho gh12, where h12 equals to h2 minus h1 is the height between point 1 and point 2. This is in the case of a static fluid. Now we are going to study fluid dynamics. We have to study a fluid in the situation where we have a flow inside a tube. For example, we have a tube and we have in and out. We have a quantity of fluid flow with a certain velocity, at any point, what we have to calculate. And maybe we can have a big reservoir and we have a tube, a small tube. We have a difference of section between between the input and the output. Anyway, here in the fluid dynamics, we are studying a fluid with flow, with a velocity. And we can take into account the height between any 2 points and also the velocity of V1 and V2. So we must have an equation where we have P1 minus P2, and in this equation must be in function of the height between 1 and 2 and the velocity V1 and the velocity at the point 2, V1 and V2. The second point, here we are studying ideal fluid. We have a big difference between the ideal fluid and the real fluid. In the case of real fluid, we have to study, or we have to take into account, the viscosity of the fluid. If you study the motion of an object inside a water or a quantity of water, it's not the same if you take oil, because we have a difference of viscosity. So in the case of real fluid, we have to add the coefficient of viscosity with the calculation. But in the case of ideal fluid, we have to take the following 4 assumptions, or 3, okay? First of all, the fluid is non-viscous. What I mean, it means we have to neglect the internal friction inside the fluid. And an object can move inside the fluid without any resistance. This motion, it can be, must be the same for any fluid when I talk about the ideal fluid. So the density rho will be the same, okay, for any fluid in the case of ideal case. The second point, the flow is steady. It means we have a steady state. The velocity of the fluid at each point remains constant. For example, here we have a tube. We have in and out. if we take any point, for example, point 1 and point 2, in this case, we have a steady state of flow. The velocity v1 is constant during the time. The velocity v2 is constant during the time, and v1 is not equal to v2. We have a difference of velocity, but we have a constant velocity at each point. This is the second assumption. The third one, the fluid is incompressible. It means we have the same density at each point inside the medium, where the density at the point 1 is equal to the density at the point 2. Okay, now let me go to the calculation. Now the objective here, we have to find a relation between P1 and P2. With this relation, we take into account the height h1 and h2, and also we take the velocity v1 and the velocity v2 into account. So we have h1, h2, v1, v2, and p1 and p2. So let's go to do the calculation. Uh, in general, in this chapter, I want to study only two equations. First of all, we have the continuity equation, where I calculate the relation between v1 and v2, the velocity at the point 1 and the velocity at the point 2. And we have Bernoulli equation is to find the relation between p1, p2, h1, h2, and v1, v2. We have to use the continuity equation and Bernoulli equation together to simplify the calculation and to calculate the unknowns values. Now, let me explain these two figures. First of all, I want to explain the configuration. First of all, we can have one tube. Inside, we have a flow of water, of fluid. This tube can have the same section, where the section at the point 1 is equal to the section at the point 2. We can have the same height. It means we have an horizontal tube. We can have, for example, a tube like this. It means we have a different height at 1 and 2. H1 is not equal H2. And also we can have a different cross-sectional area, where we have a small tube at the point 1 and large tube at the point 2. So I want to take a general case where we have a different cross-sectional area at the point 1 and 2, and we have a different height at the point 1 and 2, like the figure to the right. Anyway, let me explain first of all the figure 1 and 2. Here we have a small section at the left side and large section at the right side. In general, we have to take 2 points. The point must be at the middle distance at the x of the tube. For example, here I can take 1 point here and 1 point here. In this case, to calculate the height, you have to put the x at the lowest point here, okay? And h1 is equal to h2. So in this case, we have a horizontal configuration where h1 equals to h2. The second point, the area, the section of the tube as a point 1 equals to a1 equals to pi r1 square. R1 is the area, is the radius of this tube. Or it can be calculated in function of the diameter equals to d1 divided by 2 square. And the same for the for R2 and D2, we have A2 equals to pi R2 square equals to pi D2 divided by 2 square. Okay, this is the first point. The second point, during a time delta t, okay, we can say time interval. During a time delta t, we have a volume of water will flow inside the tube. We can say the initial time at this point and the final time at this point. So during a time delta t equals to T2 minus T1, we have a volume V1 flow inside this small tube. And we have the same volume. We can say the initial point here, T1, the same T1 here, and T2, the same T2. We have the same time interval. So we have the same volume V will flow in at this side, because you know we have an incompressible liquid. If we have, for example, 1 meter cube go at the side inside the tube, we have the same quantity of 1 meter cube will go out. Okay, so we have during the same time, the same volume and the same mass will go in, and the same mass and the same volume will go out. Okay, and the distance of the length of V1 is not equal to the length of the volume V2, because we don't have the same area. Okay, for a small cross section A1, we have a length x1, and for a large section A2, we have a length x2. So what we have to know now, this volume V is equal to this volume V, and this mass M1 is equal to the mass M2. Okay, we can say at the same time delta T, we can say V1 equals to V2, and we can say V1 per unit time T. We have to take the same unit time, and V2 per unit time T will be the same. And delta M per unit time delta T, M1 is equal to delta M2 per unit time delta T. Okay, you know that V1 equals to, we have a cylindrical volume equals to the cross section A1 times the length of the cylinder equals to x1, and V2 equals to A2 times x2. And also delta M1, you know the density equals to M divided by V. So M equals to the density times V. So we can write delta M1 equals to the density times V1, and delta M2 equals to the density times V2. V1 and V2 are the volume of V1 and V2. Okay, here I resume that the amount of mass that flows through the cross-sectional area A1 during a time delta t is the same as the mass pass through A2 and during the same time interval delta t. Okay, the same quantity of mass, the same quantity of volume will pass during the same time interval. Okay, let me write and resume the equations. Delta m divided by delta t, okay, it can be delta m1 divided by delta t equals to delta m2 divided by delta t, can be noticed by qm. Qm is the mass flow rate, is the mass per unit time, kilogram per unit second. Okay, so Qm equals to delta M divided by delta T, and Qv is the volume per unit time, is the volume flow rate, delta V divided by delta T. Okay, you know Qm equals to delta M divided by delta T, and delta M equals to rho times V divided by delta T. And the volume equals to the cross-sectional area A times the length x divided by delta T. You know we have a steady flow. It means we have a constant velocity at any point. So we have a zero acceleration. In this case, you know the relation between x and v. X equals to v times t. So x divided by v equals to t, or x divided by t equals to v. So we can say here x divided by t equals to the velocity of the fluid at this point. We can say here rho times a times the velocity. And you know delta m1 equals to delta m2. So we can say here rho 1 times a1 times v1 equals to rho 2 times a2 times v2. As we have an incompressible fluid, so rho 1 equals to rho 2. Because we are using the same fluid, we can eliminate this one and this one. We can write finally A1 V1 equals to A2 V2. This is the continuity equation where we calculate V1 in function of V2. So if you take any 2 points inside the tube, A1 V1 equals to A2 V2. Okay, this is a constant value for any point. If I take a point here with a cross-sectional area A3, and here we have the velocity V3, so we can say A3 V3 equals to A1 V1 equals to A2 V2. Okay, and you know QV equals to delta V divided by delta T, and delta V equals to A times X divided by delta T, and X divided by delta T is the velocity. So QV equals to A times the velocity. We can write finally Q equals to A times V at any point is a constant value where we have a constant volume flow rate inside the tube. Okay, this is the first equation. Let's go to the second equation. Before the second equation, as you see here, we can find V2 in function of V1, and we can find V1 in function of V2 just to simplify the calculation and to reduce the number of unknown values. Let's go to the last equation, Bernoulli equation. Here, just we have to find a relation between P1, P2, V1, V2, H1, H2. what is the principle of Bernoulli equation? Here, if we have a small velocity, in this case we have high pressure. If we have a large velocity, in this case we have a small p. So v and p is the values will be opposite. For small velocity, we have large p. For large velocity, we have a small p. For example, if we have this tube, I give you an example. If we have a tube of water and we have a quantity of water goes out of this tube from the tip. If you put your finger at the tip, you reduce the section of the tube. In this case, you increase the velocity of the water. So for a small cross-sectional area, we have high velocity. In this case, here we have tube with A1 and we have here with A2. You know, we have A1 is small, so V1 is large. Bernoulli principle says that if we have high value of V1, in this case we have a small value of P1. Okay, and at the point 2, A2 is large. So we have V2 is small. In this case, we have P2 is large. So we have to find this relation by one equation, by one formula. We have to find this relation between P and V by one equation. It's called Bernoulli's equation. In this equation, as I said before, is a relation. I take a tube with a different A1 and A2. At this point, we have a small A1. At this point, we have a large A2. Here we have V1. Here we have V2. Here we have H1. And at the point 2, we have Y2. The equation here, P1, P as the point 1, plus rho g H1, it's a potential term because I take the height into account, plus half rho V1 square is the kinetic term, where I take the kinetic energy of the fluid into account. As you see, we have a similarity between rho g H1 and mgh. You know, the potential energy in the case of the gravitational mass. And here also we have a similarity between half rho V1 square and half mv square. Okay, so P1 plus rho gh1 plus half rho V1 square at the position 1 is equal to P2 plus rho gh2 plus half rho V2 square. You can use A1 V1 equals to A2 V2. We can find V1 in function of V2. We substitute its value here to reduce the unknowns and to calculate V2. And you can put V2 in function of V1 to calculate V1. So this is a very important relation. The continuity equation and the Bernoulli equation, you can combine these two equations to calculate P1, V1, V2, and H1 and H2. Okay, let's go to do some application. of Bernoulli equation, continuity equation, and in the case of dynamic fluid.